Hello guys, welcome back to MedZone African Motifs. We are still on our engineering science N3, and this is motion, power and energy from the question paper, which was written in November 2023 exams. So we want to see how we are supposed to attempt these typical questions. And I want to thank all those who have managed to come up with this platform so that we can be able to discuss this coming up with the question papers and so forth. So guys, let us quickly rush through our questions and see how we're supposed to answer these questions. The first part, we were given 1.1 to differentiate, all right? To differentiate, that is, we are supposed to give the difference between the two, all right? The uniform velocity and the average velocity, both are velocities, but what is the uniform velocity and what is the average velocity? That is to differentiate. All right, so as we know that the uniform velocity is on a condition where the object is moving with a constant speed, whereas the average velocity we're talking about when the total displacement is taken and the total time also is taken into consideration. So we can just say uniform, let us just see if this way, uniform velocity. Uniform velocity is when, all right, this is when the object is moving at constant velocity, all right, is moving at constant velocity, all right? So this is gonna move at constant speed, all right? Let's just write as constant speed in a particular direction, all right? That's in a particular direction, in a particular direction. All right, so that is it. Whereas if we are to check what is happening on the average velocity, whereas the average velocity, that's the total displacement over the total time, all right? So this one is an object's, all right? That's an object's total displacement. Like I said, you're gonna have the total displacement over the total time, all right? So that's the total displacement divided by the total time. All right, so you're gonna have this divided to the total time taken by the object, which is taken for the object to move. For the object to move. All right, so I think this is enough. All right, the uniform velocity is when the object is moving at constant speed in a particular direction. Okay, whereas the average velocity is an object's total displacement divided by the total time taken for the object to move. That is the idea, whether there is an increase in speed or what, the average velocity, just take the total displacement that was covered, everything as it is. All right, so that was it, guys. Then we move on to 1.2, where we were given an object with a mass of 60 kilograms. So you've got an object that has got a mass of 60 kilograms, moves in a straight line. Take note, it moves in a straight line with a uniform acceleration according to this law. All right, where V is the final velocity in meters per second, T is the time in seconds. All right, there is something that we know about this. Let us just take our information. Remember, we are given the mass of the object, which is 60 kilograms, and also the law that this object is moving, V is equal to 5 plus 3t, which is in that's a linear 5 plus 3t. That's a linear, we are talking about a linear movement. In that case, we are told that this is in a straight line. In a straight line, that's a linear function, meaning to say, according to our velocity time graph, we know that this is our velocity in meters per second, and this is our time in seconds. We're supposed to have something like this if it is starting at 0. But as we know that from this formula, we also have this in our formula sheet. Let me just show you before I have this so that you can also be with me. If you check here, we've got this formula. Take a closer look on this formula. V is equal to, because you're told that this is the formula for V. So check this one. V is equal to what? U plus AT. Exactly, this is the format that we have here. This is the format that we have here. V is equal to U plus AT. What does it tell you? It tells you that the U, which is our initial velocity, is 5, right? A, which is the acceleration, is positive 3. That is what we are told. So, meaning to say our object is not starting from 0. No, it is starting at a certain point at 5 meters per second, but is moving in a straight line. So that is how our object is moving. And the acceleration there, we can even see that according to the formula, our acceleration is what? Is 3. So it's a positive there, 3 meters per square second. So it is accelerating. We do not know when it is going to end, but it's going to correspond per each time that we are having, per each time. Maybe after 1 second, you can say this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and so on and so on. We do not know where it is going to end. But at each point, the velocity is going to be changing because V is given by a formula 5 plus 3t. So meaning to say when t is equal to 1, the velocity is not going to be 5, it is going to be above 5. When the time is 2, the velocity is going to be above. When time is 3, and so on and so on, the velocity is affected by the time, because this one, our acceleration is constant. There is a constant acceleration. So this is not changing. This is what we have here. It is a uniform acceleration. So meaning to say our acceleration is not changing. The only thing that is going to change is the final velocity, the velocity with time. The velocity is affected with what? With time. According to this, V with what? With time. These are the variables that we have. It's only V and T. These are not changing. The initial velocity is not going to change. The acceleration is not changing because we are told that it's a uniform acceleration. All right? But that is not part of our question. Let's answer our question. I'm just explaining so that you also understand where this is coming from and where are we going. So the question was calculate 1.21, the initial velocity of the body. All right. The initial velocity of the body, like I said, this is our U. We can even take it from our formula here, U, which corresponds to what? To 5. So that's our initial velocity there. U is 5, and you know that velocity is measured in meters per second. If you want to take it from the calculations, from V is equal to 5 plus 3t, initially, we know that the time is supposed to be at 0 initially. That's an initial condition. Our initial condition is that the time is supposed to be at 0, not the velocity, no, but the time. The velocity can start at 6, at 7, at what? At any velocity. But the time when you're starting, it's 0. That is the only thing that we can be assured of. So if our time is 0, it means 5 plus 3 times 0 is going to give us 5. So that's our V is going to be a 5, whereby V is representing the velocity when t is equal to 0. And when t is equal to 0, that becomes initial velocity U in what? Meters per second, right? So that's the formula that can give us the velocity at any particular moment, okay? Then as you can see, it's 1 mark. There's no need for you to calculate these ones, okay? So you can see 1 mark there even for what? For the acceleration of the body. Why? Because we know from our formula, we can take it here. Acceleration of the body is 3. The A is corresponding to 3, and it's a positive there. That's 1.22. So our acceleration is 3, and we know acceleration is measured in what? Meters per square second, right? So that is our acceleration in this case, okay? So that was our condition of the question. Then let's move on. The displacement, take note, the displacement after what? 5 seconds. Displacement after 5 seconds. So here we've got 2 options that we can take into consideration. All right, like I said, after a certain time, what is changing? It is the velocity, 1.23. The final velocity, because after 5 seconds, we are now at this point. So the velocity is going to be affected there. All right. So it's either you're going to use the formulas or you can simply use the area under the graph. But if you are to use the area under the graph, it means you must find the velocity that corresponds at what? At 5 seconds. So we've got two options there. Remember, we need displacement. That's the displacement after 5 seconds, all right? After 5 seconds. So meaning to say, if we are to use the area, we can see that this is a trapezium that we have. I'm going to show you another formula. This is the trapezium that we have. And from the area of a trapezium, we know that the displacement is simply equivalent to what? To the area. And the area of a trapezium, I told you guys from our N2, it's half the sum of parallel sides times the perpendicular height. Meaning to say here, we have got the sides that are parallel, which is we are referring to the 5 here, and this side of the other velocity that we do not know. So we've got this side and this side. So that's why I said we need to calculate the velocity that is going to correspond at what? At 5 seconds. After 5 seconds, what is the velocity there? So from our formula, V is equal to U. V is equal to 5 plus 3t here. 5 plus 3t. We are saying our time is now 5 seconds. So V is equal to 5 plus 3 times 5, which is what? Which is this time 5 seconds. So we are going to obtain the velocity there of 20. This is 15 plus 5, which is 20 meters per second. So it means at 5 seconds here, the velocity corresponding here, it's what? It's 20. So when you are using half sum of the parallel sides, which are these sides, these ones gonna be 5 plus what? 5 plus 20. So this will be half sum of parallel sides. So that is half of 5 plus 20 times the perpendicular height, which is the height between the sides which are parallel, which is this one, which is at what? At 90 degrees. We are talking about this distance of 5 meters. Of 5 units. All right. So that is going to give us the displacement. If we take it this way, that means we are going to obtain our displacement as 62.5. All right. Let me just bring the calculator here so that we can have this together. All right. Let me have the calculator here. All right, so this is going to be given as half of, oh, sorry, I did not share the calculator for you guys. Sorry for that. Sorry for this. I want us to, calculator is already there. So that's half of 5. So that is 5 plus what? 5 plus 20, which is 25. Okay, let us just write 5 plus 20. Okay, then we're going to multiply by 5 like this. So this will be, all right, because my calculator is fixed to 3 decimal places, let me just go back to the normal mode. I have to press 8, then 2, which is like this, 62.5, all right? So that will be 62.5 in what? In meters. So this is our displacement, all right? Of which we could have used the formulas, all right? Because like I said, what is changing in this case, it is the velocity, but the final velocity, but the initial and the acceleration are not changing. So taking into consideration that we have got the initial velocity, so this is another way that we could have just calculated using our formulas, knowing that we have got our u, which is 5 meters per second, and we also have the acceleration of 3 meters per square second, and we are given the time, that our time is 5 seconds, and we are asked to calculate displacement, which is s. How can we calculate s? We can take this from our formulas. If you take a closer look, I'm just going to show you your formulas again. We've got these formulas. S is equal to ut plus half at squared. We also have this one. All right, so I'm just going to start with this one. Let's see how it was going to help us to find this, okay? So from this formula, the first one that we saw, it is stating that S is equal to ut, that is ut plus half at squared, all right? Meaning to say we can use this formula from our linear motion, that is u, the initial velocity 5 times the time, which is 5 plus half of the acceleration is 3 times the time, which is 5 squared. Just like that, everything is there and the formula is clearly given. So this was the best thing to do. So the first one was going to give us 25 and the second one 37.5. Then we combine everything. That will be 62.5 in meters. All right. So that is the idea there. Still on formulas, we saw that there is this formula that they gave us here. I want you to check this one. If you check properly, there's this one. 2as is equal to v squared minus u squared. But this formula now is going to limit us, all right? I want you to see it is given as 2as is equal to v squared minus u squared, like that. And to find s, it means we're going to divide by 2a. Divide by 2a here, divide by 2a here. It means s is going to be v squared minus u squared over 2a. So if you were using this information alone, because that was the information that we were given, this one, this v was not there. Remember, we calculated this v because of this method that we used of the area. All right. So meaning to say this v, the final velocity, was not there. So if you were to use this formula, you were to calculate v first, because you do not have the final velocity after, because this is after what? After 5 seconds. So we have to calculate, all right? We have to calculate what? V after 5 seconds. So just like what we did here, we are not going to calculate this because already we calculated this. So we are going to calculate your final velocity like this. Then after that, you take your value, which is the 20. So our final velocity there, from our calculation, we got 20 there. So it's s is equal to 20 squared minus u. Like I said, u is not changing. That's your initial. That's where you started from. All right. Your starting point is not going to change. All right. What can change is the final, but your starting is, or you already started there. All right. At 5 meters. All right. Over 2 times the acceleration, which is 3. So that's it. We are going to still have the same answer for the displacement. And that was going to give us 62.5 in meters. So all these answers were for displacement, right? Just for displacement. I mean, all these methods is just for displacement. So it's up to you guys to choose wisely the method that you understand how to work from that method. All right. So let's check the other part of our question. That was now to have or to calculate here 1.24 the kinetic energy after 5 seconds. The kinetic energy after what? After 5 seconds. All right. They have to mention the time. Why? Because the kinetic energy, as we know that it is controlled by the velocity. All right. So this is 1.24 in this case. Like I'm saying, the kinetic energy, we know that it is controlled by the velocity. Oh, let me just show you the formulas. Let me not act as if this is something that is from somewhere here. We've got here our kinetic energy here. The change in kinetic energy is given by what? Half m times the change in what? Times the change in velocity, which is the mass times the change in velocity squared. All right. That is the formula that we can take into consideration for our kinetic energy. We do not have a straightforward formula, but that is the one that we are going to use. The change in velocity, meaning to say, is just velocity squared. So like I said, it is affected by what? By the velocity. All right. So if it is affected by the velocity, then they have to mention the time. That's why they mention that it is the kinetic energy that we're going to have after 5 seconds. And as we saw that the kinetic energy is given by half mv squared. And we are told after 5 seconds. Why after 5 seconds? Because the velocity there is going to change. We have to calculate the velocity after 5 seconds. So if you were to use this method, already you calculated the velocity, meaning to say, oh, there's no need for you to calculate this because already this velocity, remember, it was calculated after what? After 5 seconds. So if you have already calculated this, there's no need for you to calculate again. But if you haven't calculated this, maybe you used this method here. This is the method that you used to calculate what? The displacement. Meaning to say you were not going to calculate this V. There was no way because the information was already there. So meaning to say you are now forced to calculate that V from this one because they need the velocity after 5 seconds, all right? But already we calculated our velocity, we're not going to waste much time. We're just going to take this as it is. So our velocity is equal to 20 meters per second. After what? After 5 seconds, we calculated this. So therefore, our kinetic energy from the mass that we are given, remember the mass of the object is what? Is 60 kilograms. So therefore, our kinetic energy is going to be given as half times the mass in kilograms, which is 60, times the velocity squared, which is the velocity after 5 seconds, which is what? Which is 20. So that is 20 squared like that. So that was going to give us the kinetic energy, all right? And that was going to give us 12,000 joules like that, which is 12 divided by 1,000, that's 12 kilojoules, okay? So we could have calculated our kinetic energy that way, okay? Let's see the other part of the question. Now they want us to calculate on 1.25 the change in momentum, right? And that's 2 marks for that. So as we know that the change in momentum is also affected by the velocity. So meaning, okay, that's 1.25. We know that the change in momentum is equal to the mass times the change in velocity. Meaning to say our velocity has changed. Remember, we started with an initial velocity of 5 meters per second. And finally, after 5 seconds, our velocity was now at what? At 20. This was now our velocity. Remember, it was now at 20 meters per second. So the velocity has changed. So that's why they need us to calculate the change in momentum. But they have to mention in 5 seconds because it happens in what? In 5 seconds. That is where our momentum changed. Our velocity changed for that particular time. All right. So we are working under 5 seconds there. All right, so under 5 seconds, everything is there. So we're just going to put in our values here. That is the mass of the object. Remember, the mass of the object is not changing. That was the mass of the object here. M is 60. So that is going to be 60 times the change in velocity. That means the final velocity minus the initial velocity. The final is 20 minus the initial, which is 5. All right, so that was going to be the idea, which is 60 times what? 15. If you subtract here, that's a 15. And if you multiply this 60 by 15, what are we going to get? That's 900. So it's going to be 900. Remember, the mass is measured in kilograms, the velocity in meters per second. So that's kilogram meters per second. All right. So that's our change in what? Momentum. Okay. That was the idea there. That was the idea of the question. So as you can see, that is first part. Then we move on to 1.3. 1.3. All right. So on 1.3, there we are given a flat belt drive. There we are given a flat belt drive transmits 36 kilowatts. This is the power. So it transmits the power 36 kilowatts from one shaft to another shaft. All right. The belt speed being 72 kilometers per hour. That is the speed of the belt. V is 72 kilometers per hour. As you know, this is supposed to be in meters per second, and 1 meter per second is equal to 3.6 kilometers per hour from our N2. So you're going to divide by 3.6, and this will give us 20. That's a 20 there. So, right. So this is going to give us 20 meters per second. All right. Like I said, it's supposed to be in meters per second. And also we are given the belt. All right. Which is a width of 22 centimeters. So the width of the belt is 22 centimeters. Transmit, take note, this is the allowable tension. All right. So it transmits 12.5 Newton per millimeter. Take note, per millimeter of what? Of its width. So this is the allowable tension, that one. We are given an allowable tension which affects the tight side. So that is 12.5 per millimeter belt width. Take note, per millimeter belt width. Okay, what does it mean? It means it's affected per unit width in millimeters. So our width here is supposed to be written in millimeters so that it can be affected here because it's per millimeter belt width. So remember 1 centimeter is 10 millimeters. So you're just going to multiply by 10 here. That will be 220 millimeters. All right. So you're going to have our width in millimeters. All right. So the first question was 1.31. Calculate the effective force in the belt. All right. How can we have the effective force? All right. That's 1.31. We want to have the effective force. All right. Take note, we've got the power. We also have the velocity. And if we check from our formula sheet, we've got the formula that connects the power and the effective force. Here, it states that the power is equivalent to the effective force times the velocity. So you can take advantage of that because we want effective force. We have the power, we have the velocity. So that was the best formula for us to take into consideration that the power, its effective force times what? Effective force times the velocity. All right, so let us just have this. Power is the effective force times the velocity. And as we want the effective force, we're going to divide by the velocity both sides. That means the effective force is going to be the power over the velocity. Our power, 36 kilowatts. So that is 36 times 10 to the exponent of 3, which is kilowatts, over the velocity in meters per second, which is 20 meters per second. So this is going to give us the effective force. All right, that was going to give us 1,800. All right, so this is 1,800 in what? In Newton. So some, they can use TE for the effective force as the effective tension is just one and the same thing, or you can just write as what? As FE. All right, so that was it in this case. Then 1.32, it was to calculate the slack force, all right, which is the tension that we have on the slack side. That is the force on the slack side, all right, 1.32. That is our T2, the slack side. Remember, it's what is T2. This is our slack side. Then for the tight side, remember, it's T1, all right? That is for the tight side. So what can we do? All right, about the tight side, we can have it from the tension. All right, always the allowable tension here that we are given, this statement here, it gives you, or you obtain T1 from there. So this gives you the value of T1, the value of T1, which is the tight side. You are going to obtain the force from the tight side from there. Okay, so what is the relationship? It follows that the tight side force, which is T1, is equal to the ratio or whatever allowable tension ratio that we are given times the belt width on that unit that you're given. So since it is given that is 12 Newton per meter, right? This was 12,5 Newton per millimeter, all right? So it's going to be 12,5 Newton times per, we need to say per each 1 millimeter. It's like this, all right? It's like this, guys. It's like this. 12,5 Newton is equal to 1 millimeter. So when it is 2 millimeters, what do? You multiply by 2. When it is 3, you multiply by 3. So we imagine for 220 millimeters of the width, because it's per belt width, per 220, what is going to happen? You're going to multiply by what? By 220. So that is the idea there. So this gives you the tight side. Like I said, you obtain the tight side from what? From the allowable tension. So that was going to give you something like 2,750 Newton from your tight side. Okay. Now that we have got the effective force, remember we calculated the effective force, and we know that there is a relationship between these two. All right, now let's get back to the formula sheet again so that we do not actually, this is somewhere from, no, we have this here. The effective force is equal to T1 minus T2. So we can take advantage of that because we have it. We have it. All right, so from effective force is equal to T1 minus T2. It follows that in order for us to have 2T, we're going to transpose T2, which is the slack side. This side, it becomes a positive. It gives us T1 minus the effective force. If you bring the effective force, that side is going to be a negative. So that means T2, which is the slack side force, is equal to T1. We got our T1 here as 2,750 minus the effective force, which is 1,800. So this is going to give us the force that we have on the slack side, which is T2. All right. I explained this before. So I just hope now understand this. All right. So this is the force that we have on the what? On the slack side. So this is the slack force. Okay. So this is your questions, guys. They ask like this. You just have to be used to the typical questions. How are they asked? And how do you answer those typical questions? So that was it, guys, from Maths on African Motives. Till we meet again.